Okay, there we go. All right, so 2 times ago, we talked about K-maps, right? K-maps will be on the exam. I'll definitely put a K-map on the exam. They're actually quite a bit of fun, right? Do we remember how to do K-maps roughly? Where you draw up a square. Okay. So there's one trick, right, that we don't want to forget. We label these like so, but the third one is 1, 1, and then 1, 0, right? Because they all need to be logically adjacent, which means you can only change 1, 1 at a time. Same thing goes for this direction, right? So if you're filling in the, if you're filling in the K-map from a truth table, you'd fill it row 1, 2, 3, and then 4. Question?
Is there going to be a K-map with more than 4 variables?
There will not be a K-map with more than 4 variables. And we will cover today how to do that, but it's not going to be on the exam. Yeah.
Just a question on like if there's like a row of 3 ones, so would you circle set of 2 and another set of 2?
Yes.
Okay.
Yeah.
Because I was on the homework, there's a problem like let's see. So you want to circle as many as you can?
Yes, as long as it's 2 to the n and there's no weird bends in it. So it can be a row, a cube, right? So this will give us some good examples. What do the x's mean?
Don't care.
Don't care. Yeah, so let me erase, well, whatever, I'll keep it. So, a couple examples of circles that you could make, right? On this one, just as review, you've got an entire row, you've got a cube, or if you're paying a lot of attention, you can actually wrap all the way around and grab 8 together, right?
So is it okay to not, like, could you just do wrap 4 and then the other 4, and would that be okay? Or do you need to find, like, the biggest amount?
You want to find the biggest amount.
Okay.
Because what that means is the larger the circle, the fewer terms that are going to be in that portion of the final expression. Right, so once I have these circles, and I just want to write some function out of this, I look at the circles that I have. And so in this case, really, I only need the big one that covers 8, and then this little one that covers these 4. I have all of my ones covered, right? So doing the biggest circles I can has 2 benefits. One, it minimizes the number of terms in each. So it's going to be the sum of products, right? The product expressions will be minimized, as well as the number of sum terms being minimized by having the largest possible circles. So here, because I only need 2 circles, I only need 2 terms to sum together. And then I look at these and see what doesn't change over the entirety of this circle, right? So here, from this, so if I look at the square, the 1 doesn't change, and this one doesn't change. So that's C, right? And B. And then C is 1 and B is 1. So we have BC. Yeah.
Could you do all 6?
Can't do 6.
Okay.
Why can't I do 6?
Not 2 to the n.
Not 2 to the n.
Oh, it is. Right. Okay, right. I just thought it was a group of 2.
Yeah. So if I've done 4 and I end up with 2 terms ANDed together. Now I have 8. How many terms am I going to have ANDed together?
One.
Just 1.
It's just, you know,
And so, yeah, it's just D naught. Right? That's K-maps. Drawing that, yeah.
Now, what about this thing where they circle the zeros and then they do like a product of some?
Excellent question. So this one is what we call a sum of products. The other option, we can do the same K-map doing a product of sums, which what that means is F is also equal to, well, let me grab a different color. Orange, excellent, orange works, where I also need to worry about the zeros. Well, instead of worrying about the ones, I care about what the zeros do. So in the case of the zeros, right, I've got a whole row, which we like. The X, I don't care. So you might be tempted to do something like this circle and then this 0 and that 0, or this circle, right, and this circle. But what you want is the minimum expression. So if you notice, you can do this on those two. And the X, I don't care if I include that in my circle or not. I can, but I don't need to. So again, I have 2 circles, but they're smaller circles in general. But because I have 2 circles, I have 2 terms. But this time, they're ANDed together with each subterm being ORed together, right? So in this one, I have not CD. Does everyone see that? Not C or D. And we're going to have 3 in this one, right? Because it only has 2.
So, Professor, there's something that, like, in the book, it was like, it does opposites, so it would be like C, not D, right? Because you do like,
Oh, is some product with some swapped?
there's something like that that was like super confusing.
Yeah, sorry, you are absolutely right. So you may notice I never use these, and you will very rarely, and there's an actual like real design reason for that. And it's that most circuits end up implemented in NAND, and it's really easy to take this equation, implement it in NAND logic. But I like that you called me out, because
I'm just worried about, like, if we see this on the exam.
Yeah,
You know,
yes.
like, are we gonna have a possibility of seeing?
there is a possibility of a product of sums. Now, the nice thing that you called me out for is I can use this as a good explanation of why, is if we remember our good friend De Morgan's theorem, right? If I were just to take one of these equations and invert it using De Morgan's, right? Then it would turn it in this or into an and, this and into an or, and then we'd put bars over it. So that's where this comes from.
Okay.
So that's why if we had, and this is where the mistake came in, it looks like not CD, but instead that. Yeah?
So for the second term, you get less variables if you use that for 0, right?
Yes. So what he's just pointed out is that instead of using this circle and that circle,
oh.
good catch. Also, if you didn't see that one, you could also do this circle, right? Because that X can be a 0 if you wanted to. And then that would simplify at least one of the terms. But because of your sharp eye, we've got all 4 terms in that one. And we look again at what doesn't change. Looks like D is there, and what's our other one?
B naught.
B naught. D and B naught. So we would change this equation. And we have D and B naught, but we flip those because we're the other way. And those, unless I screwed something up, should be identical if you drew out the truth table for those. So you can always check your work with the truth table. That's interesting. So this shows in both cases that says promising, that A doesn't matter, right? So A is a completely trivial variable in this map. Okay, so let's expand this a little bit. This is obviously limiting a little bit if we want more than 4 variables. So there are 2 ways to do this, and I kind of hinted at it in the last class for one way. Today we're going to cover the other way. It is called map entered variables, or you'll also hear it variable entered maps. I don't know which way is like the correct term. I've seen it both ways, and I don't use either. That's the secret. But if you end up taking 3610 from Dr. Brown, he will definitely use them, so I want to make sure you're prepared for that. Let me jump to that section. They're not that bad, really, once you kind of get into them. There we go. This is section 7.3. So another way that you could say draw a 4-variable map is start with a 3-variable map. So it's going to be A, B, C, 0, 1, right? And then instead of having just this being a function of 1 or 0, it can be a function of another variable. So now we have, to add one more variable, we now have 1, 0, D, or D bar. We have 4 things that can go into it. Now this looks horrifying, but the nice thing is you can circle things together as long as they satisfy, well, let's just do it this way. So if you say X or Y is Y, well, where in this map do we have that? Well, D bar or 1 is 1, right? Same thing with D or 1 is 1. But let's not be that way. We've got a bunch of 1s. Let's use them, right? But this is only the first step. And what this is saying is that here I have, since I have D, it is D ANDed with the 1 that would go into this expression, or D ANDed with this implicant. Remember that term? Implicant just being the circle. So what you're looking at is a how do I describe this? Sorry. This is just step 1 of what we need to do. So this gives us some of our equations. But now we need to reduce our map a little bit. And we're just going to do that now that we have the circles with all the D's in it. We're going to go ahead and say on table 7.1, there's a just set of rules of how to replace these things. And if it's a 0, it stays a 0. If it's a map entered variable or an expression, D, right, that also goes to 0. So let's do this one at a time. I'll do it a little more explicitly so we don't lose track of things. And this is actually pretty nice because it just boils down to a couple of rules. So 0 stays 0, 0 is 0. Map entered variables also become 0. And then 1s, so if it is 1 and the sum of the coverages, right, is 1, it becomes a don't care. And 1, if the sum of the coverage is not 1, it becomes a 1. So in our cases, this one and that one stay 1. And this one becomes a don't care. Pretty sure. So now we have our second map. And this is all just from table 7-1. There's no magic or anything. And then we have to solve for this map, which is really easy, right? We just have 1s and we don't care. Now we take the sum of products from this table ORed with this one. So F is simply, well, what is this circle? We have A, and as I said, it's ANDed with the term that you're in here, right? And D. Right, because if it wasn't a map entered variable and that was just a 1, this would just be A. But instead it's A and D. Or, well, C doesn't change and B doesn't change, so B, C, where C is 1 and B is 1, ANDed with D. Right? B and C, D. And then, is it A naught? B.
But it would be D naught because the one circle is a D naught.
Oh, D naught. Sorry, I thought you were saying B naught. Nope. Apologies, my bad. And then you want to look at this map, and you're just adding one more term. And AB C doesn't change, A doesn't change, and we don't need to do anything with the map entered variable because it's not part of this anymore. So that's your 2 steps. Do what you can with the map entered variable, follow the replacements from table 7-1, which I will allow notes on the exam when we get to this. This is not on the upcoming exam, but I will allow notes. So you don't have to memorize the table even, that's on, but you will want to have it. And then jump over to this guy and OR it with it. You had a question?
Yeah, so I just wanted to go through this again. So if it has a 0, so you have your original table with the D naught or whatever variable that they put in.
Yeah.
And then you want to reduce the map. So if there's a 0 in it, it goes to 0. A map entered variable or expression goes to 0. So your D naught and D will go to 0.
Yeah.
And then 1 and the sum of the coverage is 1. So if it's like circled with something, that's the one that I'm.
Yeah, no, I'm right there with you because it is never as clear as I want it to be. I'll be straightforward. I don't use map entered variables because if you end up in a situation where you have more than 4 variables, you're going to let some computer do it for it. So I'm going to read for just a moment and make sure that I can figure out the right way to explain the annoying subgroup. So this is going to go through the process on, shoot. So you want to have the book pulled up so they actually have the right page number?
Yeah, 105.
105, thank you. So they're pointing out that cells, I will label the cells here at this point so that we can talk about this. 0, 1, 2, 3, 4, 5, 6, and 7. And so they're pointing out, right, cells 0, 1, and 2 stay there. And then what we care about, the weird one, right, are 4, 6, and 7. So in cell 7, it is 1 covered by a D loop and a D bar loop. So what you're looking at is D or D bar. Well, D or D bar is always 1. Yeah. These ones are only covered by B, right? So this is saying the sum of the coverages. So the sum of D bar and D or D bar is 1. This is just D. And D is not always 1, and therefore it's not, the sum of the coverages can't be said to be 1, because the sum of the coverage is D. Yeah.
So what about if it's connected to D and D, not D bar?
Still not 1.
Will be just
Yeah. Only if the sum, which really means or together, is 1. Don't worry, we'll go through this pain together as we go through a couple of examples to make sure that we can figure this one out, right? So, sorry, I have to pay attention because I want to make sure the exam is Wednesday, and my priority today is make sure we at least get through the review so we don't get confused there. This class ends at 11:45. I want at least half an hour, 11:15, so I've got 20-ish minutes. Yeah.
That's in class, right?
It will be here in class. If you fall ill the morning of, be prepared to like get a doctor's note or something. I don't want you to come to class. We will make it happen. Don't fall ill on accident because I have to write a new exam for you if you do that, and it makes me grumpy. But if you fall sick, don't come. It's really fine. We'll cover all that in 20 minutes after I finish. The intro to MEMS, we'll come back to this as well as review, and K-maps as well in general because they're such an important concept going forward. You'll use them as a design tool in various other things down the line. I'm not going to harp too much on them. There will be questions on them, but it's not going to be like an overload of these variable enter maps because I don't find them as important as other faculty members in this school do. And a difference of opinion is fine, but I've just never, I wasn't even taught these when I was in this equivalent class. So if I get a little bit flustered when I'm up here staring at the board, it's because I haven't done these types of problems in front of a bunch of students before, and we'll work through it. So if I do something wrong, call me out. I'm not embarrassed. Okay, they have a nice example that we're just going to go through on example 711. Okay, this is going to give us the nice pain of having a 5-variable map, right? So that one we've been dreading a little bit. We need a 5th variable, and we only know, well, let's pretend we only know how to handle 4 variables in a K-map. And I will probably be nice because I would hate to do it, and so I assume you'd hate to do it. I will stick to sum of product variable enter maps rather than product of sums as well, just because, you know what, I don't care that much. E bar, E, E. Okay, well, this is quite a mess. I guess I can explicitly write the zeros. Okay, so let me make sure I can see the green on the camera. Yeah, that's fine. It's not great, but it's there. Circles. What do I want to circle? What do I want to circle? What implicants do I want to start circling? Right. Where should I start? What's the biggest one that you can see?
You can only get two of them together.
So,
But there's multiple stuff.
oops. 1, 1. Well, remember that I can, in a variable integer map, I can also get e's in the circle as well.
So up at the top, in the middle, there's a box.
Yes, absolutely. Excellent. There you go. Right, behind her. What's the next one I want to do? There you go. Well, there in the back right corner, what do I do?
The E naught to the one above it on the middle row. Yeah, that one is one above it.
Can we do better than that? The whole column, absolutely.
Well, can we do the whole column because it's E, and E naught?
Oh, good question. Good point.
That's what I was thinking. I could just do the E naught.
See? That's a good point. I almost forgot that rule because. So, learning opportunity. Yeah, they don't like us to circle E and E naughts together. So lots of E naughts, E's together would be fine. Totally forgot about that. Thank you for being smarter than I am. Then we've got, I'll keep the simple ones, right? And then I think this poor little E naught's got nobody next to him, right? Okay, so let's assume that you guys can write this equation, right? So for each one of these, it would be like E bar and whatever this would be if he was a 1, right? Do we get that part of it? So then this one would be E and something, whatever that sums out to. Then we're going to draw this. Oops, let's switch back to green. Okay. That's the ugliest map I've drawn in a while, but that's okay. So we know that zeros stay as they are, right? What do we do with the E's and the E bars? Zeros. So 0, 0, 0, 0, 0. That's lots of zeros. Good catch. Okay. Then, now we need to start looking at this weird sum of coverages thing, right? So, this one, it's just E bar, right?
No, it's E and E bar.
This one?
Oh, that one. Sorry.
Yeah.
Yeah, that one.
So what does that mean for us?
That means that should be a 1. Or, yeah, a 1.
Yes. Because the sum of the coverage is not 1. So we care what it is. These two ones. Actually, are they both X? Let's double check.
Right.
Yeah, they are.
Because they are in E.
Yes, because we have an E in the square and an E bar in the row. I've got one more one. What's this guy? Just a 1. I don't think there's anything fancy we can do with this map, right? We just pretty much have to take it as is with minor simplification. And then write out the equations. Do you guys want me to take the time to go through all writing out the whole expression? Raise your hand if you would like me to write out the whole expression. Okay, enough of you do. We'll puzzle through. Okay, so let me start from scratch. Yeah. Let me make sure I'm not doing something weird going off the screen. Okay. Let's start with the hardest one, this E bar guy, right? So we know we're going to do E bar ended with something. What is the expression that he ends up with?
A naught, B naught, C, D naught.
Yes. Does everyone see where that comes from? Right, from the ABCD. Now we have another expression going on. Let's grab another bad one, where this is going to be E ended with, well, we do a similar thing, right? So we know that these are going to be true, so we're going to have C, D naught, and then only one of these, which is going to be A.
So A, C, D naught.
Absolutely. We've got two more circles to do. This row, does someone that's not comfortable with this want to try it so that they can be sure? No? All right, any other volunteers? What is it, guys?
C naught D.
Yeah, C naught D. And what's it ended with?
E naught.
Now, I've done it this way, putting the E's at the front. I usually prefer to put them in alphabetical order, but I just want to be clear how we're writing this out. Last square, right? That's the only one we haven't done. What do we got?
B, C naught.
C naught. So we got B and C naught. Absolutely. Totally agree. Okay, so those are our terms from step one. Step two no longer uses the map entered variable, right? So we can just do or this stuff. Yeah.
Didn't we miss the E bar and one in the middle there? We only have
Oh, I
6
absolutely
circles,
did.
and we have 5 circles.
Yes. So you pointed out I missed this circle. We don't want to miss circles because we miss points when we do that, right? So we've got B and D and A. Yes. Okay, so A, B, D, all ended with E bar. And then all of this gets ended with these two circles, which these just no longer have that E term at all. And so we can just say that this is A, B, and C. Or this guy, which is C, D, and A bar, C bar, D. Did I do that one right?
Yeah, so from what I understand you do is you do the first equation, like the first K map is with your variable E, and then your next map is you take away all of the E's and you just do the variables that are would be there without the E's, I guess. And then you combine them?
Yes.
Okay.
Yeah. And combining with just fours. So we can then go look at the answer and make sure that I didn't screw up somewhere, because this is an example in the book. So we should have an AC D bar E That's here. We should then have an A bar, B bar, C, D bar, E bar. So a big one. A bar, C bar, D bar, E bar with a C. There we go. A, B, D, E bar.
It's supposed to be a D down below.
Oh, this one. A, B, D, E bar. Got that one. C bar, D, E bar. That one. B, C bar, E. That guy. Then A bar, B, C bar.
That one should be,
Which one?
the first one. That should be A bar, D, C bar.
Okay. And then A bar, C bar, D. That one. Looks like I got checks over all of them, right? There we go. That's map entered variables. It's not horrifyingly painful until they like to do something like, well, maybe you don't want just a single variable inside. Not working very well. Sure. Let's draw our 4-variable map in a different way. Right? This is still just a 4-variable map drawn in a different way. Now these ones are a little bit tricky because you can't treat these ors quite the same together. So what you end up doing is connected circles. So we know we want to match these with a 1, right? But this is how you end up doing it when you're ORed together. You end up with C bar or D circled with that 1. But when you have C and D, you can. Because this expression, C and D or 1, C and D bar or 1 is still equal to just 1. Right? Because if I'm ORed with 1, I get 1. That's not necessarily true with the ORs. Oh shoot, I erased that one. Okay. Then the step 2 is what we would normally do, but we have to start looking at, sorry, where's my green? Zero, 1, 0, 1. Okay, so we know that zeros stay 0. Now let's look at what happens to this expression. What do? What do I do in the map entered variable when it is an expression or a map entered variable? Turn it to 0. And we do the same thing with the other one. And now we have to figure out this one, right? And so the sum of the coverages is CD bar or C bar or D. And we have to see if this is true, right? Is it 1? Well, either I have D or D bar, right? So these two are linked. And then I have either C bar or C, so these two are linked. And so in any combination, either D is true, C bar is true, or CD bar is true. So it is always 1. Do you want me to write out the truth table for that we can prove, or do we see it? Right, I can't make this not 1. So that becomes what if it is 1? X. And there's not a lot of simplification we can do to that, right? I mean, in fact, there's not really any simplification we need to do that, right? Because it's X. I don't care if I circle that or not. So there we go. So our only terms we have to worry about is these ones, which then I need to start worrying about the terms inside of them. So in the first case, I have this circle. B is what's not changing. But then I have to deal with the map entered variable, right? And I and this with the map entered variable. What is the MEV? In this case. Or, well, now I've got 2 ones where in both cases it's the A that's not changing, right? And I need to AND them with C bar and then AND it with D. So I have A ANDed with something or A ANDed with something, and it's C bar D. Right, so I do those two, the ORs separately. And then because I don't need to circle the X, I don't need to add any terms from here. The figuring out whether to keep it as a 1 or turn it into X is probably the most obnoxious part of these things. And the brute force way is always to write a truth table, right? So you have an expression, you can just write 0, 0. Like if it has 2 variables, it just means 4 lines in your truth table, and you can figure out if it is always 1. There are sometimes tricks that you can see to do it, or you can use your Boolean algebra, right? We have a couple of those rules that kind of reveal whether it's true or not. And make sure I have time to do this long, painful one. 5 minutes. We can at least start it. I have a question for you guys before. Would you find it more helpful to just cover this more in, like, more examples in class after, what, a week from today, after we come back from the exam? Or would you just like me to make a video of it? Or maybe send links of videos to it for the map entered variables.
I think the video thing works for me.
So you have one for videos, any other opinions?
I like both ideas.
You like both ideas? I mean, I can do both ideas.
I think getting as many problems, because I feel like the book doesn't give us enough like material to like really understand it, you know what I'm saying?
Okay.
But like anything that you can give us
Yeah.
is awesome.
Okay, that's fair. I will do my best not to leave you guys high and dry on this map entered variable thing. And I will try not to let my disdain for it wash off too heavily onto you guys. Okay, so we can have, all right, to make sure that it's visible on the screen. We can have 6 variables, right? And it's probably best, you'll notice something that I end up doing is I keep trying to take the shortcut of not bothering to write everything up, but then I get myself confused and lost. For that reason, I expect learning from, or I encourage you to learn from my mistakes and just label everything from the get-go. It makes it a little bit easier to not get lost in your math. Now, this one, I'm now already regretting it drawing it as small as I did. You may find in the future having multiple colors of pen or pencil is helpful. Oh shoot, helps if you draw this right. This is an F bar. And an F bar here if you're taking notes. Okay, so circles that we can make in here, remember we don't get to circle the E bar or F bar like together, but I can take just the F bar part of that. Similarly, we have something like this one's interesting, actually. I'll get to that in a second. So E and a 1, F bar, F. Okay, I need to go back to this original rule so that I don't make myself confused when I explain this. So if you recall, if you have something like D or 1 equals 1, I am allowed to circle it. So in this particular case, we have an interesting situation where what is EF bar or F bar? So EF bar. Sorry, I'm trying to puzzle out this one. This is one that I don't quite understand. They're allowing us to make that circle. And I'm going to take a pause there because we're going to start further review rather than taking the time to figure out why the math works out for that one. And then we'll come back to that on Monday, and I will have better explanation. Yeah, this is a perfect time to start. This, map and variables, not on the exam. So I know you're all going to flush that out of your brain and forget it, and we'll start from scratch on Monday. I will try not to flush it from my brain so that I can do nice, clear explanations of that. The exam is hopefully not going to be anything surprising to you. It's really going to be very similar to the homework. The only thing that is not going to be homework-like is I will ask questions that come out of your labs. So as I go through your labs and see things that you aren't maybe understanding, I'm going to stay up late tonight. I am going to not be able to grade all of your homeworks, but I do want to get you answer solutions to them. So I will stay up late tonight. I will pump out a bunch of answer solutions to the homework so that you have answers to review to. Now I know the book has selected solutions in the back, right? I don't have the selected solutions in my version of the book. How many of the questions, do you have like a rough feel for the percentage of the questions that actually have answers back there?
I think it like jumps around, doesn't
Yeah,
do like,
Yeah, and some of the one that are listed like A, B, C, D, it's like, we'll give you B.
Oh, okay. So it's a small selection. Okay, I will pump through and start getting some answer solution out there. I think I've graded your guys' homework 1 and 2. Pretty sure. And so those ones you have the answers to, and then the other ones I'll get to. Things I'm not going to do to you is I don't care about adding or converting this from binary to decimal or to hex or anything. I really don't care about the radix points. That's not going to be on the exam. There's going to be no radix points conversions. There will be hex to decimal, decimal to binary, binary to hex, and so on and so forth, right? All those conversions will be on there. They will just not involve radix points. I have a list of things that I need to make sure I tell you. 2's complement will be on there, right? So if this is a 2's complement number, what is the value of this digit? Yeah, it's negative 2 to the n, where n is 1, 2, 3, 4, 5, 6. Negative 2 to the 6, right? And then I add everything else to it, right? Don't forget 2's complement is that, and I will tell you that if it's 2's complement, I may ask something like, this is a 2's complement number, but I need it in 8 bits. Please convert this 6-bit 2's complement to an 8-bit 2's complement. What you can't do is just add 2 zeros, right? Because this is pretty clearly a negative number. This is very obviously not a negative number. What's important is recognize that it is obvious not, right? So that might be a type of question that I do. I might do something like add these 2 numbers. Binary addition. I might give you hexadecimal numbers and tell you to add those together. How would you do that?
In hex or binary or both?
If I told you to add 2 hex numbers together, what would you do?
Let's see.
14, so say ABC. Am I thinking the wrong thing?
Yeah, well, you could do it that way. You could add the hex numbers, or you could convert it to binary and add the binary.
Oh,
Right, you have to convert it back to hex for the answer.
Then convert it back to hex. I will accept either way, right? Because you may recognize that in hex, what is 9 plus 2? Yeah, right. So you may recognize the addition, or you may have to do conversion. Either way is fine. I'm not going to judge you on the method unless I specifically ask you for a specific method, right? The answer is what's important. Showing your work is very important because I like to give you guys partial credit. I can't do that unless I can see your work. You've seen this one a lot, especially in labs. What is this? Ohm's law. I will ask you questions on Ohm's law. So if I show you an exam, a question like so, and I ask you, I could ask you multiple questions. What is the current flowing through the resistor What is the current flowing through the resistor when the switch is open?
So you do current is equal to.
So, yeah, so you convert this to I equals V by R, but there's a trick here. It's a trick question. 0. There is no current flowing through the resistor. Because where does it go? It goes from VCC to here. Nothing happens, right? So the other question is, what is V out when the switch is open?
volts.
5 volts, exactly. So now let's say I have an input to this switch. What is the relationship of V out to V in? So this goes high, the switch closes. What is the relationship between V out and V in?
It's like opposite, so the inverted.
Yeah. V out equals V in, or V out equals not V in, right? I could, similarly, ask the same series of questions with a switch. As switch replaced with an, what type of device is this? And what, specifically what type?
CMOS?
More specific.
No.
4 letters.
CMOS or NMOS?
NMOS. PMOS has a bubble and actually wouldn't work right here for reasons that you won't learn until, I don't know what class actually, 2260 maybe, I hope. Just so we're clear, when we use gates like this, where we have NMOS and PMOS, this becomes CMOS. The C just means complementary. That's all CMOS is saying. I may ask you, what is this device? It's an inverter. Let's erase a bunch of stuff since I'm getting scattered all over the place. I may ask you something like, given this device, and then I might draw like this one and one with an NAND gates and something else, implement some function, right? And so then you would draw, like if you needed, I don't want to spend too much time drawing everything out. So if I had something that I wanted A, B, or C, and I gave you, instead of these inverters, I gave you an OR gate. And I gave you 2 of these devices, say, right? I gave you, sorry, 1 of these devices and 1 AND gate. Then you would have to draw this circuit by wiring them together, right? So I'd have A and B. C. And that's F, right? I might have you draw that up. I could do it with devices like this. I could do it with gates like this. You should know AND gates. OR gates, NAND gates, NOR gates. NAND and NOR, right, have multiple forms. If I do something weird like this, B equals what in relationship to A?
There's a buffer.
Yep, exactly. Because two inversions counter each other out. All of the Boolean algebra that we went through, right, the simplification. So if I write something like, and then ask you to simplify that, could you do it? And it would probably be a little more hard than these ones, right? So this one, you would just factor it out. And then C or C bar is what? 1. Right. De Morgan's law will be on there.
Do we get notes on this test?
You get notes.
How much?
Let's give you one notebook. No, so there's a trade-off, right? The more I give you, the harder I make the exam.
Right.
And so I don't want to give too hard of an exam. I don't know, it can be fun. Or I can make a nice hard exam and just make it open notes, open books, whatever you want. But the question is, how many of you don't have a physical copy of the book? Only one. I'm still waiting. Oh, 2. No, I know. The bookstores are notoriously awful for universities. So it's 2, no one else.
You could add, like, put your own notes, like maybe like Ohm's law, like Morgan's theorem, and like a bunch of other stuff on like the back page of the test. I don't know.
Yeah.
Because that's the thing, like with me, I like the Morgan's theorem and some of the Boolean algebra steps is like what I get, like what I would have my notes on.
Yeah.
And like maybe like some other like, what was this thing about like some of the equations for, I don't know, what was it, like the timing thing, or whatever it's called, where you do like time takes.
Oh yeah, the delays.
Yeah, the delays.
Yeah, propagation delays can be on the exam.
I don't know.
Yeah, I'll give you ample amounts of notes. Let's say 1 page of notes front and back, or you can do 2 pages that are just single-sided. So you get 2 pages of notes. So plenty of notes, no book. You should understand truth tables. You should understand how to take a truth table and put that into a K-map and then solve the K-map, right? So K-maps are used for simplifying the circuit. If I say, write the minimum expression for F using a K-map, all that's saying is draw the biggest circles you can on the K-map, right? Because the largest implicants that you can draw on a K-map result in the minimum expression. Nice gate drawing, K-maps. You guys had a question, I really like this question, that was something like, here's a 2-input AND gate, turn it into a 3-input AND gate. Something like that, maybe it was a NAND gate, right? I like that type of question. It'll be draw out the logic of the gate. There might be something talking about timing and the propagation delay. I feel like I'm missing something that I didn't write down, so let me pull this up real quick. I will tell you now, I'm not going to ask you about the charge in an electron. You can ignore that stuff from chapter 1. That's not something that's, I don't know, useful to have memorized. It's useful to understand, but not necessarily to memorize. Conversion stuff is chapter 2, chapter 3. Oh yeah, there might be some stuff about ADCs and D to A's converters. I probably won't ask you to do something like this chapter does. Let's like prove the Morgan theory by exhaustion. That sounds exhausting, so I won't do that to you. But I will have you use De Morgan's theory, right? I may ask you, like I may draw up a circuit and have you write the truth table for that circuit. You should know the difference between sum of product and product of sum expressions, and be able to draw simple gate circuit architectures from, so if I give you F equals ABC or AB not C, you should be able to draw that using gates. That's more or less all of it, it looks like. There's no map entered variables, so those things, K-maps, and maybe some stuff out of the labs. Any questions?
I've got a question, but I think I'll talk to you. Well, I think it's a typo in the book.
That seems entirely likely.
Like it's throwing me off with this propagation delay thing on page 77. I'll probably figure it out.
No, it's fine. I mean, we've got a couple minutes, so if there's something that's throwing you off, it might be throwing other people off.
Yeah.
Got 5 minutes. So, chapter 7?
Yeah. Oh, chapter 6.
Chapter 6.
Page 77.
So I'm sorry, I don't have page numbers. Can you give me like a figure number that it's close to?
The example 6.3. Well, it's not example 6.3, but that's closest
Okay.
to it. I can show so right here.
Okay, then what's the issue?
So there's this. Let me show you. I think it's gotten.
So it's just after 6.3?
Yeah.
You know if it's in fan out?
So it's got no, not fan out. Like it's next to the relation.
So this table?
I'm gonna go up there. It's got this business hours.
I feel like this is really weird on the Google. Yeah, you might have to come into office hours.
Well, let me show you what's going on, because it says the longest path is business hours to U2A to U1A to U3A. But then down here it's saying, okay, start at U2A, and we'll give us that, and it says U2, U1, U1A is down here, so I
Oh, yeah.
this is a typo because it's supposed to be U1A. U2A, U1A should be one, goes U3A.
I think you're probably right. But the nice thing is the U1C, yeah, that's all the same delay, so it almost doesn't matter.
It's hard for me to understand what's going on right there. Like, because I can't follow, you go through here, but then.
Yeah, so I think you're right that it just labeled the wrong gate. So the main takeaway on that, if I give you guys, I mean, it doesn't matter what the gates are, right? Any type of gate. So I'd give you the delays for whatever I fill in the blank with these gates with, right? And then ask you to find the longest, or just ask you what is the propagation delay, right? So the propagation delay then is the longest path. Now let's take a simplified version and say that all gates have the same delay. What is the propagation delay? What path do I follow? Yeah, C, because it goes through 1, 2, 3, 4 gates. So that's all you're looking for is the longest one. And I might give you a table that has propagation delays. And maybe this gate has a really long delay and these ones are all really short and it's actually that one and you have to add up the math and figure out what one's the longest. Or maybe not, right? I will not put typos in my exam to the best of my
So
ability.
now, like with assertion delay and de-assertion delay, there's like something with inverters and there's something with the other gates that doesn't apply. But like, can you
Yes.
talk a little bit about assertion delay, like how you define?
Yes. So all assertion and de-assertion delay is how long it takes to react to asserting the signal. And de-assertion is how long it takes to react to de-asserting the signal. In an inverter.
But now, are we talking about the input or the output?
Exactly.
That's what I'm.
In an inverter, we care about the input. The assertion delay is asserting at the input, which means you're de-asserting at the output. Yeah, you're defining assertion and de-assertion as it pertains to the inputs of the gate.
And that's for all.
For
gates.
all gates, because that prevents any confusion about the outputs.
Okay.
Because there's like the NAND gate, which is, well, it's ANDed and it's inverted, and then, well, let's just care about what happens if we're asserting. Is how long does it take to react to an assertion at the input?
Okay, so that's the beginning of.
Yeah. If that's fine. I'll do that.
I don't know. That's like assertion and de-assertion. Like I do not feel solid on that at all. So,
Okay. Well.
But no, that helped at least a little bit. So
Okay.
I'll look back at my notes and stuff.
Other questions? As we're basically out of time.
Are we doing lab 5 today?